Cool. Hi, everyone. Um, Thank you all for coming. I'm Alex Reinking, and I'm very excited and honored to be presenting at my very first CPPCon. If we haven't already met in the hallway track, you might be wondering who I am and what I do. Well, I'm a programming languages and compilers researcher at UC Berkeley. And I'm still working on my PhD, but in a nutshell, I design and analyze domain-specific languages, or DSLs, with high performance in mind. So if you aren't sure what I mean by that, just know that DSLs are programming languages that are specialized and restricted to best meet the needs of a particular domain. The goal of a DSL is to exploit those restrictions to give programmers faster performance, easier maintenance, safety guarantees, and so on. Importantly, DSLs won't let you write just anything. I don't think you can write a web server in CMake, and if by chance you can, then you probably shouldn't. Instead, DSLs really focus on making some part of a larger software system easier to handle. It's nicer and more portable to write CMake than raw shell scripts and batch files. It's also more efficient to use a well-engineered parser generator than to read a bunch of textbooks and write down parsing tables for your language yourself. In the programming languages world, we draw a distinction between internal DSLs that borrow the host language's syntax and toolchain, and external DSLs that supply their own. But in either case, you've probably used a few. Eigen3 and Boost Spirit are popular C++ internal DSLs for linear algebra and writing parsers, respectively. And then CMake, Makefiles, Bison, SQL, and even regular expressions are external DSLs that most of us have encountered at some point or another. And that brings us to Halide, which is the subject of today's talk. So Halide is a hybrid of the internal and external DSL approaches. It's embedded in C++, so in that sense, it's just a library like Eigen is. But on the other hand, it executes code by JITting, or by producing C-ABI-compatible object files. So in that sense, it's more external. The problem that it helps you solve is optimizing dense numerical kernels, like those found in image processing, computer vision, machine learning, and artificial intelligence. It does this through a powerful application of separation of concerns. In Halide, you define what you want to compute separately from how you want to optimize it. So before I accidentally take all of the credit for Halide, I want to acknowledge the incredible open source team backing Halide. My advisor, Jonathan Reagan Kelly, and my colleague, Andrew Adams, created Halide in 2011 when they were at MIT. My own personal role in the team is twofold. So first, as part of my PhD research, I'm working on publishing a mathematical proof that Halide programs will never crash and that its optimizations are safe. And then second, I work on the build system, testing, continuous integration, and the release cycle for the team. I also want to emphasize that this isn't a talk about some new or unproven technology. The amazing people that I work with have made Halide into the system of choice for the Google Pixel camera and the Adobe Photoshop layer compositor. When you snap a photo on a Pixel phone or edit a Photoshop document, you're using Halide. We've implemented faster neural network layers than in TensorFlow, faster blurs than OpenCV, faster matrix multiplication than Eigen, and a faster Fourier transform than FFTW, which styles itself as the fastest Fourier transform in the West. In fact, because YouTube uses Halide at scale to re-encode video, when this talk and all of the other CPPCon talks this year get uploaded to YouTube, they will be processed by Halide. So with that out of the way, let me briefly summarize the rest of the talk. We're going to discuss the main challenges in fast array processing, what matters for performance, what trade-offs we make, and how Halide helps you optimize for those factors. Then we're going to talk a bit about Halide's architecture and how it integrates into your programs and builds. But we're not going to be diving deep into architecture-specific details or picking apart assembly sequences. We're also not going to cover every feature in Halide. We only have an hour together, so I want you to take away something from this that applies outside of Halide 2. There will also be a few times when I will pause for questions. Please ask them. This topic is subtle and sometimes complicated, and no question is sort of too small to make sure that everybody's on the same page. Now, Without even thinking about digital signal processors and other specialized accelerator hardware, I want you to think about your CPU. It is incredibly complex. To optimize your programs for it, you have to reason about multi-level caches, vector instructions, multiple cores, and the costs and benefits of hyperthreading on those cores. You have to think about superscalar and out-of-order execution, branch prediction, and the list just goes on and on. If you do throw a coprocessor into the mix, then you have to think not only about how to optimize the code that runs on the other device, taking into account all of its architectural details, but you then also have to think about how to optimize the communication between it and the CPU. And if there's anything we know to be true in computer science, it's that programmers, even experts, even me, we're notoriously bad at predicting performance. Half the time, our optimization efforts do nothing, and it seems that the other half, they make things worse. Still, there are some go-to strategies we can look at. So imagine that each one of these squares is some unit of work that your program has to do. One of the simplest optimizations is to divide independent work across independent CPU cores. Of course, you need to have opportunities for this in the first place, and there are issues with hidden dependencies, like false sharing. But by and large, if you add processors to a problem with enough independent work to keep them all busy, you should expect a proportional speedup. Another optimization that might be less intuitive is to recompute values instead of loading them from memory. Remember that each level of cache is slower than the last until you hit DRAM or main memory. So if your values aren't cached, it can be a net win to do some extra work. This is actually a very old idea, and it goes all the way back to rematerialization work in register allocators in the 1970s. But it's actually still very relevant to today's vector instruction sets. So suppose you're modifying some array using vectors of width 4. If the array's length isn't an even multiple of 4, like this one, which has 14 elements, then you'll step 1, 2, 3 vectors out before finally reaching the end. Now, with only 2 squares left, you can either shift inwards and recompute a small amount of overlap, shown here in bright yellow, with a single vector instruction, or you can switch to serial code and execute 2 slower instructions in a different code path. Most of the time, we'll prefer the former because the inward shift can be computed without branches and without bloating the code. Finally, we get to the last big optimization opportunity, cache locality. Suppose you have 2 stages of work where the tasks are independent in each stage, but there are some dependencies between the tasks, as shown by the arrows here. We could go breadth first and compute all of the values in step 1 before any of the values in step 2, committing those all to memory in between. Or we could interleave the computations of step 1 and step 2. And then the memory written by step 1 will still be fresh in the cache when it's read in step 2. Ultimately, locality is a function of reuse distance. We want to reuse values as quickly as possible to optimize for the cache. On the other hand, it isn't obvious how you can parallelize this fused 2-step process. That interleaving looks pretty hopeless from a parallelization perspective. We can't just pragma omp parallel 4 our way to victory here. Instead, what we can do is break the dependency chain by introducing some redundant work. The red squares here mark where work was duplicated from the other side. And we could continue to break this problem down by introducing only a small amount of redundant overhead per thread that we want to use. And then this gives us the best of all 3 worlds. We can keep multiple CPUs busy, each one accessing its caches in a nice local way. And we didn't have to introduce very much redundant work to do it. Trading off between locality, parallelism, and redundant recomputation is at the heart of optimizing any numeric pipeline. The general principle is to strive for locality within threads and introduce redundant work strategically to break dependencies. It's a delicate balancing act with no simple heuristics, but it's the one that Halide helps you perform. So you might be thinking, this is great knowledge for library writers, But application developers can still get great performance by composing routines from highly optimized libraries like Intel's Math Kernel Library or OpenCV, right? Well, the short answer is no, because there's no way to fuse across the stages of computation. Every time you finish calling a function, you sync all of your data back to RAM before calling the next one. This is slow for the same reason we just saw with the locality example. There's no way to rearrange the computation between the stages and get small reuse distances. In general, optimized kernels compose into inefficient pipelines. Okay, so why not make C++ compilers do this work for us? There are a few good reasons. The first is that the space of possible optimizations is extraordinarily large and complicated. Making one decision that looks good locally might make the optimizer miss a much better opportunity down the line. Experts optimizing code by hand try countless alternatives before landing on the one that works the best. Second, some important optimizations are not legal in C++. Compilers aren't allowed to simply change your malloc sizes or reorder calls to external functions or try to optimize your memory layouts. They have to obey the rules of the language. The most beneficial optimizations are those that carefully fuse many stages of computation together. C++ compilers are not typically able to discover these sorts of global reorganizations on their own. And finally, from a theoretical standpoint, C++ is rightly Turing complete. That means that C++ can do absolutely anything. But by contrast, all Halide can do is express feed-forward array programs, and that makes it much easier to analyze. So for the rest of this talk, we're going to use this running example that sort of typifies the kind of program that Halide helps you optimize. It's called the two-stage blur, and it's a particular instance of the abstract example that we just saw. As the name suggests, it's going to take an input image and make it blurry, so no surprises there. But what might be a bit unconventional is that it's going to first blur the image horizontally. In code, we blur a pixel by computing an average of the pixels around it. In this first step, we compute the horizontal blur by averaging a pixel with its neighbors to the left and to the right. That gives us this intermediate step here on the right. Then, we do the same thing on the horizontally blurred image, but vertically. So now we average the neighbors above and below the final pixel in the horizontally blurred image. In the end, this is effectively the same as blurring the full 3x3 box around a pixel in one giant step, but splitting it up into two stages like this does less arithmetic overall. Now, as with all things in computer science, there are edge cases, but in image processing, they happen to be very literal. If you're trying to blur the pixels around the edge of the image, you'll find that some values are missing. You could skip those pixels, but it would crop a 1-pixel border off of the image. Since we don't want that to happen, we just extend the boundary by repeating the outer edge to keep the image size the same. That's highlighted in orange in the second step here. So let's try to write this in C++. Imagine that we've already got a struct called image that wraps a std vector and exposes a two-dimensional operator parens to access its elements according to the width and height. This is definitely slide code, and I don't want to dwell on the implementation of this image struct too much. But just assume that the image struct does the right thing for the purposes of this example. The input will be represented by a const reference to such an image struct. Then, we can get started with a boundary extending step. We create an intermediate image that's got extra space for the border. We make it uint16 instead of uint8, because we don't want the addition in the averages to overflow later. Then, we loop over all the uninitialized points in the padded image and assign them to the closest values in space from the input. C++17 makes that easy, since it adds the clamp algorithm that we use here. If you aren't familiar with it, clamp simply compares the first value to the next two arguments, which are a lower and an upper bound. If it's less than the lower bound, then it uses the lower bound. And if it's greater than the upper bound, then it uses the upper bound instead. It's a very helpful algorithm for ensuring that you don't read an array out of bounds. Then, in the horizontal blur step, we create another intermediate image, this time a bit narrower than the padded image to account for the shrinking boundary. We loop over all the points again and average the neighbors like I explained before. Pay careful attention to the loop bounds. We iterate from x equals 1 to x equals the width of the image, since we're always writing to x minus 1 in the body of the loop. And finally, we do the same sort of pattern for the vertical blur. Now, gluing all of this together isn't too much trouble, and I'll give you a second to take it all in. Now, we're writing C++, so this should be fast, right? We take the input by reference, so no copy there. We ought to get an RVO for the result, so no copy there either. We've got loops that can probably be automatically vectorized, and so the stars should align for us. But life isn't so simple. If the image struct uses a row major memory layout, so that adding 1 to x adds 1 to the pointer into the stood vector in blur x, then this code will write a pixel value to a different cache line on every iteration. This is about the worst performance you can get on this example without going out of your way to do something weird. On my machine, running this on a 4 megapixel image takes about 100 milliseconds, which is not very fast at all. Fortunately, there's a simple fix. Just swap the loops. You don't need to make any changes to the assignment since all the loop iterations are independent. Now you'll access consecutive cache lines, which is much better for the CPU. If you do this, then it drops to 8 milliseconds on the same image, which is a 12 to 13x speedup, a full order of magnitude. If you imagine memory being laid out left to right and top to bottom, then you can clearly see the issue with the traversal order. This is one of the few times that you can tell something will be slow at a glance, since it never accesses memory in a nice local way. If you continue down this path and keep on optimizing, you might eventually end up with a mess that looks like this program. You'll have to trust me that it does the same thing, but it does it with parallelism from OpenMP, that's the pragma omp parallel 4 at the top, and SSE intrinsics inside the loops. It's also locality optimized by fusing the stages together and tiling so that we can cut down on memory usage and have simpler for loop extents. But rather than pick this code apart, I want you to think about 3 questions. First, is it portable? And I don't mean across compilers or CPU architectures, because we already know that it isn't. It uses x86 and compiler-specific intrinsics, and OpenMP, none of which are standard C++. But is it portable across different x86 CPUs with the same compiler? The answer here is also no. Different CPUs, even in the same generation, will have different cache sizes. What's fast on a consumer-grade Intel i5 will not be optimal for a Xeon released in the same year. Next, is it correct? How could you tell? There's actually a subtle rounding error here, and did you spot it? What would it take for you to notice, and how long would it take to fix? Finally, is this code maintainable? Based on the previous 2 questions, I hope you'll agree that the answer is no. This code has actually already bit rotted. It's using SSE, not AVX. It has fixed tile sizes. When it was written in 2011, it was pretty good, but you shouldn't copy it into your own program today. What sets Halide apart is that it has good answers to all 3 of those questions, and it does it through a really clever separation of concerns. The first thing you do when writing a Halide program is to define the algorithm, which specifies what to compute. It's a declarative specification of what to do, not code that will immediately run. As such, it doesn't care about loop bounds or memory or traversal orders or anything else. It just serves as a single source of truth for what your pipeline should return. Later on, you'll specify how you want to optimize it, and then you get a chance to run it. So let's see it in action on the blur pipeline. First, we'll declare a func called input. A func in Halide is conceptually a mapping from array locations to values, but with indeterminate bounds. For the functional programmers among you, note that every func in Halide is pure. That is, it has no side effects and always returns the same values at the same points. So the boundary extending stage looks almost identical to what we saw earlier in plain C++, only it's just the assignment statement. Again, we used clamp to keep the inside of the bounds of the original input, but remember that the input func is still a placeholder. The eventual width and height will be determined when we actually feed an image through the pipeline, not right now. Similarly, The variables x and y here are symbolic variables that don't have specific integer values at this point. It happens to be that repeating the edge to extend the boundary is such a common thing to do in image processing that Halide provides a helper for it. So we'll just go ahead and use that here to make things easier to read. Now, we'll define the funcs for the horizontal and vertical blurs. The horizontal one reads from the upcast image, and the vertical one reads from the horizontal image, same as before. Excuse me. Once more, the glue code is fairly minimal. Nothing new besides the variable declarations and the cast back down to 8-bit in the result func. Remember that since Halide is just a C++ library, this is valid C++ too. We're just using operator overloading to get a natural syntax. The func and var types are normal C++ classes. So now is a great time to stop and answer any questions you might have, because we're about to jump into the deep end optimizing this. I'll wait just a minute for some questions to roll in if there aren't any, and then we can move on. And I'll also wait a little bit to account for the delay on Remo. So we have one question that says, on slide 28, you said that clamp from C++17 is used. What if the company uses Visual Studio 2008 and there's no support for C++17? Is there any workaround? So on slide 28, the code that I was showing was the C++ code. I'll pull up the slide. That I was using to demonstrate how you would write this in C++. This code isn't something you would actually want to use, and you can always replace clamp by an equivalent set of min and max computations, instructions, or macros. The use in Halide is, again, just sort of tangential. I used clamp here to both show off a cool C++17 feature and to make the code fit on the slide. However, I will point out that Halide as a DSL and as a C++ library does require C++ 11, and we don't test it on Visual Studio versions prior to 2015 anymore. So your mileage may vary if you're stuck on 2008. I got another question. Does the DSL follow some sort of C++ standard? It is, for all intents and purposes, a normal C++ 11 library. You include its headers, you link to its shared library, and you just write normal C++ code surrounding it. So let's continue along. So the other side of the Halide coin is the schedule. The relationship between a schedule and an algorithm is somewhat similar to the relationship between a CSS style sheet and an HTML document. A schedule is a companion to the algorithm, and it defines an order of execution by referring to the funcs inside of it. As we'll see shortly, it controls vectorization, tiling, inlining, parallelism, and more. The scheduling language provides some strong guarantees. Applying a scheduling directive will never change your program's output, and without manually disabling checks, your program will never crash either. So keeping this code in mind, let's talk about how to schedule it. And we're going to focus in particular on the input 16 func, the blur x func, and the result func. For the purposes of this, think of the result func as being blur y plus the downcast back to uint 8. The next few slides are all going to follow this same format. On the bottom left, we have the Halide schedule code that's applied to our blur algorithm. On the right is the imperative pseudocode corresponding to what Halide will generate based on that schedule. On the top is a visualization of the programming running on a smaller image, and at the very top, we have performance numbers for running it on a 4-megapixel image. The checkerboard pattern indicates an uninitialized buffer, and the blue and yellow triangles track where the pipeline is reading and writing, respectively. This schedule is equivalent to the bad C++ code we saw earlier. It uses two directives, compute root and reorder. Compute root means that Halide should compute all the values of that func and store them in a big array before anything else tries to read from it. Then the reorder directive sets the loop order to be y innermost and x outermost. we can actually see the program run for a minute to see what it's doing. So I'll let it run back around to the start here. So first we can see input get copied, padded, and upcast into input 16. And it does this one pixel at a time. And it's going in the slow against the cache line direction. Then we can watch as wide rectangles of input 16 are read to compute single pixels in blur X. Finally, we can watch as tall rectangles of blur X are read and downcast to compute the final result, the pixels in result. So now this schedule is the same as the faster C++ code we saw earlier with the corrected loop order. Because Halide either knows or controls the memory layout for every func, it gets traversal orders right by default. Again, we can watch as input gets copied and padded into input 16, but this time in the cache-friendly order. And we can watch input 16 get blurred horizontally into blur X. And then finally, we can watch blur X get blurred vertically, all using the straightforward memory pattern. And again, we see that this is 8 milliseconds, or a 13x speed up over the naive code we just saw on the previous slide. So if you choose not to schedule your pipeline at all, then every func will be inlined into the result. Because this pipeline is short and memory bound, this is actually not the worst schedule. It's ever so slightly faster than the previous one, taking 7.5 milliseconds instead of 8. We use inlining as the default schedule in Halide because it encourages users to break down their algorithms into small funcs with zero overhead. This enables scheduling only the funcs that seem relevant up front, but still allows for incremental scheduling without being slow by default, which would be the case if we took compute root as the default schedule. Notice that in this schedule, the intermediate buffers for input 16 and blur X have disappeared completely. Now 9 pixels are read for each pixel of the result, which means considerably more computation will be done here than in other schedules we'll examine. Halide provides another directive that automatically vectorizes loops for a given vector width, helpfully named vectorize. In this case, we mark every inner loop to be vectorized with a 32-element wide vector. Remember that our funcs operate on uint16s, which are 2 bytes wide, and AVX512 has 64-byte wide vector registers, so 64 divided by 2 is 32. Halide transparently handles alignment and instruction selection issues for every supported architecture. Notice in the animation that for tail cases, Halide will do some redundant work. When padding and converting the input to the 16-bit form, the vector shifts inwards and overlaps the previous one on each row. This is the same optimization I described at the beginning of the talk, but for free. Because these are vector instructions, this is more efficient than switching to serial code for the tail case, because that would end up being up to 32 or 31 serial instructions. The generated assembly has fewer branches as a result and is smaller overall. This schedule is already pretty good, and it clocks in around 3 milliseconds and a 30x speed boost over the most naive code we've considered. This is the kind of performance you would expect to get if you were using a SIMD template library in plain C++ to optimize the inner loops. But there still aren't any locality optimizations in that schedule. The first Halide directive we're going to use to achieve locality is called tile. It breaks up the x and y loops into 4 loops, x, y, xi, and yi, where I is short for inner. Notice in the imperative code that xi and yi have known extents prescribed by the arguments to the tile call. Halide will figure out the right bounds for the plain x and y variables so that they iterate over the tiles. Here, I chose to chop up the loops for the result into 128 by 24 pixel tiles. You might wonder, how did I pick that tile size? And the answer is that I did it by trial and error, which is quick and easy to do with Halide. I tried square tiles, tall tiles, wide tiles, and I manually tuned until I landed on this. But tiling alone isn't useful until we fuse the computation of earlier funcs into those tiles. Halide provides a directive called compute_at that enables us to interleave the computations of 2 funcs by moving the loops for the producing func into the loops of the consuming func. So here, we move the blur x func into the x loop for the result, and then Halide will automatically disambiguate the variable names to avoid clashes. We can see that blur x, that's right here, is computed just before the tile loops for the result. And Halide will use this information to compute only the values of blur x that are needed for those two subsequent innermost loops. Then we can apply the same directive to input 16, and we can see that it moves before the blur x loops. And after disambiguating variable names again, like before, only what is needed for the current computation of blur x will be computed in input 16. As a bonus, Halide's bounds inference engine is able to determine that fixed size allocations are appropriate for the intermediate buffers because the tile size is fixed. It will malloc them at the start of the pipeline, but because they are constant size, you could ask for them to be placed on the stack with a special directive. I'll let this play for a minute. You should notice that the overall pattern of computation resembles the abstracted one we saw earlier on in the talk. Within each tile, we go left to right and top to bottom by vectors, and overall, we process tiles in the same way. This schedule is as fast as I could find for a single core on my workstation CPU. It processes an image in 1.2 milliseconds, or 86 times faster than the worst schedule we saw. I'll let that finish up. And now finally, this is the fastest schedule that I could find for 4 cores. It processes rows of tiles in parallel. Remember that the results Y indexes tiles, and this is a big optimization. We also move the blur X computation closer to the usage site. This improves locality at the cost of some more compute. This one was a particularly small optimization, but I think it's due to the multiple threads accessing the same memory at the tile boundaries. And now we can process this image in a mere 0.4 milliseconds, or fully 251 times faster than what we started with. That's 3 orders of magnitude. Notice that this schedule makes use of every optimization we have discussed at the beginning of the talk. It uses redundant recomputation, both to avoid slow serial code paths and to break dependencies. The independent tiles are computed in parallel, and the access patterns within those tiles are cache-friendly. The reason this code runs so fast is because it's found a sweet spot in the 3-way trade-off between compute, locality, and parallelism that's specific to my CPU. It might be the case that a different schedule will be better on your CPU. But this schedule code is only 9 lines long. That's not pseudocode on the left. It isn't a large maintenance burden anymore to write many schedules, each optimized for different hardware. Now, finding these schedules is a bit of an art form and does require some expert knowledge to understand what is fast or slow about a schedule. But a nice feature of having a decoupled scheduling language is that we can define a search space over those schedules and write programs called autoschedules to go through them automatically. The current release of Halide has 3 autoschedulers, and they're all named after the academic papers that describe their algorithms. One that's been around for a while is called Mullapudi 2016, and it gives you a decent schedule very quickly. It's good to use while you're still developing the algorithm and making sure that it's correct. The next one, Lee 2018, is optimized for machine learning and optimization tasks, where you use Halide's automatic differentiation features to perform gradient descent. This is a more advanced use case, but it's also currently the only autoscheduler that searches for GPU schedules. Finally, there's the Adams 2019 autoscheduler that uses deep learning to produce CPU schedules that are competitive with human experts in x86. There's ongoing work to bring it to ARM and GPUs too. On the blur pipeline, Adams 2019 finds a schedule that runs in 0.6 milliseconds instead of the ever so slightly better 0.4 millisecond schedule I found manually. But we got it for 0 effort. This isn't quite fair to the Adams autoscheduler either, because this is just the first schedule it returned. It can be run in a tuning or profile guided mode, where it learns by observing your pipeline. This enables you to trade significant compile time for better runtime performance, but it's actually already competitive on its first attempt. Also, I haven't analyzed this schedule in detail, but I do notice that it uses 3 levels of tiling. rather than the one that I used earlier. In all likelihood, this schedule will beat mine on a larger image because it will optimize the DRAM to L3 cache interface better. A 4 megapixel image happens to fit just inside my L3 cache. It also makes better use of some scheduling features, some that we don't have time to discuss, like the manual loop unrolling directive, or the store at directive, which enables finer grained reuse distance trade-offs. So we're a bit more than halfway through the talk. And before we dive into Halide's implementation, let me pause again and answer some questions. So, does Halide let users specify different ways, e.g. precisions, in which to perform intermediate fixed or floating point computations separately for the same kernel? The short answer to that is yes. Because Halide is staged in C++, it's possible to have a C++ program automatically generate the variants for the different types that you would want to use. We have official API support for this that I'll describe in the next section. Another person asks, can I plug in my own allocator for the intermediate buffers? I'll describe the runtime in more detail in the next section, but the short answer for that is yes, you can. Another question. Is tile followed by parallel different than parallel followed by tile? That is, can you specify parallel either within or across tiles? Yes, you can. Parallel applies to a variable name, and if you use tile to break it apart into more than into multiple variables and introduce new ones to your func, then you would have to call parallel on those tiles variables later. But if you're doing it on an earlier one, it should just commute. Slide 53. You tried for 4 cores. Does that mean we can do it faster using more cores? What about GPU support? I tested on 4 cores because I believed that testing on my 10-core workstation wouldn't necessarily be believable to the audience. I'm sure it would run perfectly well on my 10-core workstation, as long as I used a large enough image. And regarding GPU support, it is perfectly possible to write a GPU schedule for this. I just didn't do it because I didn't want to assume that my audience had GPU background. I'll just wait one more minute if there's any last-minute questions. Yes. Does the auto GPU scheduler consider upload and download time? I believe that it does. I'm not involved with the implementation of the Lee 2018 auto scheduler, but it's pretty well tuned to its use case. Once the Adams 2019 auto scheduler gets GPU features, it should perform even better. Okay, I think that's it for questions for now. Just one more second, account for the delay. Cool. So Halide leans heavily on the LLVM compiler infrastructure. So you can expect all of the good research that's gone into Clang to apply to Halide code as well. We take the Halide algorithm and the schedule and combine those into a single function in our intermediate representation. After some optimization passes, this is translated to LLVM's IR to compile to vectorized x86 or ARM code, or to graphs of CUDA kernels, and the CPU code required to launch and manage them. The full picture is a bit messier. We keep adding backends, not all of which go through LLVM. But at this point, if there's a commercial architecture you can think of, we either support it already, or it would be easy to add support, either through a custom backend to Halide or by extending LLVM. Most recently, we've been working on RISC-V and Direct3D12 as backends. We've seen a good bit of the front end already. The basic way that it works is that we overload operators to simplify the creation of syntax trees for specifying the algorithms. Because Halide code doesn't run until you schedule it, from the point of view of a Halide algorithm, the whole C++ language is const expert. For loops in C++ get unrolled into Halide syntax fragments. If statements in C++ let you conditionally include code in the pipeline, and so on and so forth. Using C++ as a host language means that we get all of the benefits of C++ for debugging Halide programs. This is a good sort of design for any domain-specific language because it avoids the chicken-egg issue of tooling and developer communities. Developers don't want to use languages without good tools. and no one wants to write tools for a language that nobody uses. Staging Halide in C++ means that most of the time I get to work in CLion or Visual Studio and use the fantastic debugging, code completion, and static analysis tools there. Once you've scheduled your pipelines, we translate it to an internal representation, which is suitable for bounds inference. And then we apply some more domain-specific optimizations before moving on to LLVM. The Halide library contains LLVM inside it, so you don't need to install it or deploy it yourself. We then either JIT compile, or output an object file and header for future linking. Because we're using LLVM, Halide pipelines are already compatible with all of the popular sanitizers, including thread, memory, and address sanitizers. So let's talk a bit about JIT mode. LLVM has a very robust JIT module called mcJIT that we use. It's cross-platform and well-tested, but JIT mode is mostly useful when the structure of your pipeline might vary at runtime, or perhaps for rapid development. This is because LLVM's optimization passes are slow, and this introduces a good bit of latency. We have a caching mechanism that offsets this a bit, but if you don't need dynamic pipelines, then the ahead-of-time compilation mode I'll discuss in a minute might better suit your needs. So this is a fully working Halide program for the blur we looked at earlier. I left out the schedule to fit it on the slide, but this should give you a sense of how little code is needed to get something working. You really do just include a few headers, check your command line arguments, and then get off to the races. There's some code in here for loading and converting images. Halide supports a wide variety of image formats, including PNG, JPEG, TIFF, and even MATLAB, and I think NumPy arrays. Then, most of the rest of the code is the same as we saw before. You define the variables that you're going to use, the functions that you're going to use, define those, and then I'll just give you a chance to take all this in. The one point that we haven't seen before and that I wanted to call out is this bit of code that actually runs the pipeline. First, we call compile JIT to invoke LLVM, but it's on the second line that we actually run the pipeline. The realize function takes a window of the output to compute. Halide pipelines have a demand-driven execution model. You'll notice that we didn't explicitly pass the input func to the result func, but instead built the whole pipeline around it, and then just used its size information to determine what window of the result to compute. So if you don't need to pay the JIT overhead, you can use the ahead-of-time compilation mode. Conceptually, this is more like a traditional compiler invocation, but since Halide is just C++ and has LLVM inside of it, you have to do it in two stages. First, you write a generator subclass and link to a special main function that we provide. This is a fairly similar setup to Google Test. This gives you a generator binary that you run to get an object file and a header. That object file can be linked to your final application, included in a static library, or linked to a generic runner that sniffs metadata about your pipeline to aid in benchmarking and testing. The object files use the plain C ABI so as not to run into C++ ABI incompatibility concerns. The generator code for this pipeline is even shorter because it can exclude the image loading and saving boilerplate that's provided for us by the generic runner. Again, there's very little magic here. We have to name the input and output functions explicitly as fields of the generator. There's some C++ template magic going on here that allows the generator base class to locate those variables. Notice that the struct blur is passed as a template argument to generator from which it derives. This is called the curiously recurrent template pattern, and it's really, really cool, especially for implementing domain-specific languages. If you haven't seen it before, definitely Google it after my talk. The only other bit of magic here is the Halide register generator macro that communicates the class name and the intended C ABI function name to the special main function that you link against. So I'll just give you one more second to look at this. Generators can also take command line parameters from the generator binary to produce variants. So you can put if statements in your generate function here that read those parameters to generate different versions of pipelines. So that should address the question that came earlier about using different types in the middle. Now, from a build perspective, there's nothing up our sleeves. You just need to step through and compile the special main and the generator, link them together into Halide, run that program, and then link the resulting registration file to our special runner. These commands are for a GCC-compatible compiler, but the process is essentially the same for MSVC. Imagine that the environment variable HLRoot points to the Halide installation path for this. The only real pain point here in most build systems is that you need to run a binary that you built during your build to get a binary that you'll eventually link against during the same build. Also, since Halide is a natural cross-compiler, we have to specify the target to be the same as the host, but we could also put a different target here. We support cross-OS and cross-architecture builds. You can compile to ARM from x86 or vice versa. You can compile to Linux from Windows too. Your machines don't need to have CUDA installed or even a GPU to generate CUDA code, and so on. Now, this is not a CMake talk, but if that sounded scary, I do want to put your mind at ease. I've personally put a lot of effort into making the build story as seamless as possible. Halide itself is built with CMake, and we provide a CMake package too. Generators are still a bit of a square peg in a round hole for CMake, but for most common cases, it's quite easy. All you do is create a generator executable by linking the Halide generator target to your sources in the usual way. Then you call our special add Halide library function that our package supplies. It will create a static library for you from your generator executable. It has a wide variety of options for more advanced build scenarios, including running an auto-scheduler on your pipeline. But this is all you need for standard cases. Finally, we link the generated blur library to the runner. The add Halide library function populates a variable with a path to the generated registration code for the runner. And then you just invoke CMake in the normal way and point it to your Halide installation directory. Finally, the last bit of Halide's engineering that I want to talk about is its runtime. Many domain-specific languages have heavy runtime requirements, garbage collectors and the like. Halide has none of that. It simply requires malloc and a threading implementation. All the pieces of the runtime can be overridden bit by bit, either through weak linking on supported platforms or explicitly calling a function that overwrites a function pointer. The malloc that it uses is a system one by default, but it can be replaced by your own implementation if you so choose. For each operating system that we support, we provide a highly tuned thread pool that's optimized for the types of contention patterns that Halide pipelines encounter. Clients have tried to replace it with, for example, Intel's thread building blocks thread pool, but so far we haven't encountered a faster one. Finally, the runtime is sufficiently minimal that it is used in industry and embedded scenarios. Qualcomm actually provides an older version of Halide as part of their official Hexagon DSP software development kit. And that about wraps things up. I hope you take away these things from my talk, though. First, performance in numerical pipelines is a complex trade-off between parallelism, locality, and redundant recomputation. Performance is counterintuitive, and to achieve maximum performance, you'll have to try many different strategies, most of which are either pointless or pessimizing. I also hope you learned about some of the benefits Halide provides. By separating algorithms from their schedules, Halide code is easier to maintain, faster to iterate on, and more portable than manually optimizing C++. Also, just this week, we released Halide 10, which includes the Adams 2019 auto-scheduler I showed earlier. I do hope you give Halide a try. Thanks so much for listening to my talk. You can learn more at halide-lang.org, reach me via email at alex_reinking@berkeley.edu, or on LinkedIn or Twitter, where my username is just Alex Reinking on both. The same is true of GitHub too, actually. I'll use the remaining time to answer questions, but afterwards I'll be hanging out in the hallway track. Ideally, I'd like to get floor 4, table 2, but I'll post the exact table in the Slack when I get there, and thanks again. Okay, so I'm seeing a few questions here. So the first one is, many industry inspection machines snap high-resolution pictures, even as big as 20 megabytes for a single picture. Is it possible to take advantage of cache for such cases? The answer is absolutely yes. And the bigger your image is, the more important it gets. Another question I see is Halide, got an upvote, sorry. Halide is written with images in mind, but can it be used with other 2D data, or is it a square peg in a circular hole? Halide was originally written with images in mind, but it has since crossed over to the machine learning and scientific computing domains too. A domain is a sort of fuzzy concept in computer science. What Halide really does is it optimizes computations over dense multidimensional arrays. So if your program fits into that domain, more likely than not, Halide will be a good fit for some part of it. I get another question. Is Halide used for commercial cases? If yes, what happens if there is any issue in code that results in a commercial loss? I'm not sure what that question means. What do you mean by commercial cases? Halide is used in many devices that are put into consumers' hands, including all of the Google Pixel phones. I'm not sure what happens if there's any issue in code that results in a commercial loss. I guess I'm not sure what commercial means for this question, sorry. Any specific tutorial you recommend to learn Halide? Yes, there is an official one on halidelang.org. There's a link to the tutorial at the top of the page. Finally, what are the best resources to learn more about the specific optimizations one can incorporate into Halide, the expert's knowledge you mentioned? So our Doxygen document contains most of the optimizations that are actually all of the optimizations that Halide exposes. And those are good enough to get state-of-the-art performance on a wide variety of pipelines. What it really comes down to is that trade-off that I talked about earlier between compute, parallelism, and locality. LLVM and most compilers are so good at what they do that basically your time is best spent reasoning about the sorts of global reorganizations that Halide helps you make. That's just kind of the state of things. So for production use cases, are the generated binaries shipped to devices or are they generated on devices? Typically, the AOT compiled Halide binaries are shipped to the devices. You don't typically deploy the whole libhalide to an embedded device. You would just deploy the small CABI object file that you generated on your build machine. Is C++ the best language to define the pipeline? Absolutely. Of course it is. I mean, what language would we want to use besides C++? That said, we do have Python bindings. So if you're in a machine learning scenario where you really want to integrate deeply with NumPy or scikit-learn or something like that, then you can use Halide from Python. That might be one reason you wouldn't want to use the perfect language that is C++. How easy is it to use Halide from, say, C? Is this a supported use case? I guess you mentioned Python now already. Yes. You can't define and compile a Halide pipeline from C, but you can absolutely use a generated Halide pipeline in C. Also, we have an output mode in the generator that generates plain C code. And this is for use when we don't have a backend available and you want to use some proprietary C compiler for some proprietary target. And that is actually also available from CMake. That is a supported scenario. Yeah. I still have 5 minutes here. Keep them coming. Of course, Halide is open source. It's on GitHub and it's MIT licensed. Oh, sorry. The question was, can we contribute back to Halide? We very much welcome and encourage pull requests. Show us weird algorithms, please. I'm sorry I don't have bonus slides for weird algorithms, but you can find a whole host of full, complete Halide applications inside our Git repository under the top-level apps folder. You'll find our faster than TensorFlow depth-wise separable convolution layer there. About memory allocation, can I optimize for memory size? Yes. The way that you do that is by controlling basically the compute at locations, the tiling sizes, and then we also have this feature called the store at location. So if you're willing to trade off more memory, you can set a store location higher than the compute location, and that will keep those values around longer, as opposed to just every time it hits the compute loop. Does it work with consumer-grade CPUs like NVIDIA GTX 1660 Ti, GTX 1070, and those? I personally develop Halide on a workstation with 2 GTX 1080 Ti's in it. So yeah, absolutely. Our build infrastructure uses actually some older consumer-grade GTX chips. I think Fortran is known for taking advantage of stronger aliasing stuff, and LLVM less so because C and C++ does not have those. How does Halide deal with that? So I'm not too familiar with the backend code, but from what I understand, LLVM actually does provide ways for you to inform its code generator and its optimizer about aliasing restrictions in the IR itself. So it's actually easier to get those types of optimizations by going through LLVM directly than it is through standard C++ code. Are supercomputing centers planning on deploying Halide installs? If so, are they worried, potentially irrationally, about just-in-time compilation? I'm not personally involved in any talks with supercomputing centers, but I would love to see it deployed. I do know that people who do scientific computing will load the Halide binaries themselves and generate AOT pipelines and deploy the generated object files to their supercomputing jobs. I've personally done that as part of a class I TA'd. But yeah. I hope that answered that question. Well, it looks like we have 1 minute left. So I want to just thank you all again for listening to my talk, engaging with me here. And hopefully I'll catch some more of you out at the conference.